There's one last part of chapter 10 that I'd like to talk about, and that is gyroscopes. This is hard to draw, so I'm going to use the slides for this. If we set this flywheel rotating around its axis, in other words, this beam here, the system will precess, orbit, and it seems like the pivot without falling. That there's a gyroscopic stability to this, and instead of falling, it'll precess around in a circle. And so the next few slides, we want to talk about why that happens. Imagine that the flywheel isn't rotating, that there isn't any angular momentum to worry about. The initial angular momentum is 0, so we hold the axis horizontal and we release it. The weight of the flywheel here creates a torque about the pivot point, and if we curl our fingers down, our thumb points in the y-axis. So that's going to get us rotation clockwise down the page, as we expect, right? If there's no other reason for it to stay upright, this whole member will just fall and, bump onto the table, I suppose. Okay, but if there is an initial angular momentum, if there is an initial angular momentum, so we've got this orange flywheel rotating with, okay, so if it's rotating, then omega points along the x-axis as drawn, and then so does the angular momentum, L sub I initial. As we release the thing from rest and gravity tries to make it fall, gravity creates a torque on the system and wants to rotate it down this way. This torque is the same as before. But now there's a momentum conservation issue going on. The sum of the torques has to be related to the change of the angular momentum. All right, if we view from above, that torque is related to the change of the angular momentum. So the angular momentum is subject to a change that is perpendicular to it. And what happens, think about circular motion, right? If we've got a mass at the end of a string, we keep applying that centripetal force to keep the mass rotating in a circle, spinning in a circle. We're pulling in a direction perpendicular to its velocity all the time. Our force is perpendicular to our momentum, linear momentum, linear force. In the case of the flywheel, we've got a rotational force that is perpendicular to our rotational momentum. And what's going to happen is, in just like linear circular motion, we have a change of direction, but not of magnitude. The torque indicates the change of direction, and for each little delta t, we get a small differential delta L in the direction of the torque created by gravity around the pivot. But it moves in the XY plane. It doesn't fall vertically. It'll rotate around the pivot in that horizontal plane. Gyroscopes are really, really neat. They have all kinds of cool applications. The digital electronic gyroscopes or accelerometers are used in your phone. They're used in Wii remotes. They are all over the place, and essentially they're all tracking the same thing: this rotational stability of a gyroscope. Okay, that's the last piece of the chapter 10 puzzle. I'll stop it here.